Have you ever just stopped and wondered what makes water, well, wet and liquid, but the air you breathe a gas? Or what's literally holding a solid object together? Well, the answer is this amazing set of invisible forces, a kind of molecular glue that decides the state of pretty much everything around us. Today, we're going to unpack these incredible intermolecular forces. And to kick things off, let me throw a puzzle at you. How in the world does a gecko do this? I mean, it's not suction cups, it's not some kind of sticky slime. The real answer is pure chemistry. And believe me, by the end of this, you'll know exactly how it works.
Now, this isn't just some abstract science stuff. Think about this. Back in the early 1900s, the only known treatment for leprosy came from this really thick, sticky oil. The problem was, it was so ridiculously sticky it was almost impossible to use. Then along came a brilliant young chemist, Alice Ball, who figured out how to tweak its properties, how to change that stickiness, and in doing so, created an effective treatment that was used for decades. She was, essentially, mastering the art of stickiness, which is really just another way of talking about intermolecular forces.
So what is it that determines if something is a solid, a liquid, or gas? Well, it all boils down to a constant battle between two opposing things. You've got the energy of particles trying to fly apart, and then you have these intermolecular forces trying to pull them together. Whichever side wins that tug of war determines the state of matter. Okay, before we go any further, we have got to clear something up. This is a super common point of confusion. Not all chemical forces are created equal, and it is absolutely crucial to know which kind we're talking about. So there are two main players here. On one side, you have intramolecular forces. Those are the super strong covalent bonds inside a single molecule, holding its atoms together. Think of them as the steel frame of a building, incredibly tough. On the other side, you have intermolecular forces, or IMFs. These are the much weaker attractions between separate molecules. They're more like weak magnets holding two different buildings near each other. Today, we are focusing completely on those weaker intermolecular forces. And when I say weaker, I am not kidding. Just look at this example with hydrogen chloride. To actually snap the covalent bond inside the molecules, that takes a whopping 430 kilojoules of energy. But to just overcome the stickiness and pull the molecules apart from each other, to turn the liquid into a gas, it only takes 17 kilojoules. That's about 25 times less energy. It's a huge difference. All right, so let's start at the very beginning, with the most fundamental force of them all. This is the one that exists between absolutely everything, from a tiny helium atom to the most complex proteins in your body. It's called the London dispersion force. Now, the most important word to remember here is temporary. See, electrons in any atom or molecule are constantly just zipping around. And because of that, just for a split second, they can kind of pile up on one side. This creates a fleeting, temporary imbalance of charge, what we call a temporary dipole. And that tiny random event, it starts a domino effect. As soon as one molecule gets temporarily lopsided, its new, slightly negative end pushes away the electrons in the molecule right next to it. This induces a dipole in its neighbor, which creates a very weak, instantaneous attraction between them. And this is happening constantly, all over the place, in every substance. You can see this effect so clearly right here. Take a look at the halogens. As the molecules get bigger and heavier going down the table, from fluorine to iodine, they have more and more electrons. More electrons means it's easier to create those temporary imbalances. The technical term is more polarizable. And what does that do? It leads to stronger dispersion forces, which hold the molecules together more tightly, and boom, you see a steady increase in their boiling points. And that brings us right back to our gecko. The secret to its gravity-defying magic trick is nothing more than London dispersion forces. I mean, the force from just one of these interactions is unbelievably tiny, but as scientist Keller Autumn figured out, when you add them up by the millions and millions, they become incredibly powerful. So how does it do it? Well, a gecko's foot is just a masterpiece of surface area engineering. Each toe is covered in hundreds of thousands of tiny hairs called setae. And then, each of those hairs splits into hundreds of even tinier tips called spatula. This creates a mind-boggling amount of surface area, allowing for millions of points of contact with the wall, and millions of tiny dispersion forces that, when added together, are more than strong enough to hold up the gecko's entire body. Wild, right? Okay, so dispersion forces are our baseline. They're everywhere. But what happens when a molecule has a permanent imbalance of charge, not just a temporary one that comes and goes?
Well, that gives us something called a dipole-dipole attraction. In polar molecules, one end is always a little bit positive and the other end is always a little bit negative. It's not random, it's a permanent feature. So they basically act like a bunch of tiny little magnets, where the positive end of one molecule is naturally attracted to the negative end of its neighbor. And this extra little bit of force makes a huge difference. Let's compare hydrogen chloride and fluorine again. They have almost the exact same mass, which means their dispersion forces are pretty much the same. But because HCl is polar, it has that extra dipole-dipole attraction. That's enough to make it a liquid at 150 Kelvin, while nonpolar fluorine is still a gas. That stickiness is just that much stronger. All right, now we get to the heavyweight champion of intermolecular forces. It's a special, super-powered version of a dipole-dipole force. And honestly, it is arguably the reason life as we know it can even exist. This is hydrogen bonding. Now listen, don't let the name fool you. It is not a true bond. It's an intermolecular force. It's a special case that only happens when hydrogen is directly bonded to one of three very specific, highly electronegative atoms: nitrogen, oxygen, or fluorine. You can remember it with the acronym NUF. This creates such a powerful and concentrated partial positive charge on the hydrogen that it forms an incredibly strong attraction to the negative end of a neighbor. And wow, this chart just shows its power perfectly. If you were just following the trends of other similar molecules, you would predict that water should boil at around -80 degrees Celsius. But of course, we all know it boils at 100 degrees. This enormous difference you see for water, ammonia, and hydrogen fluoride is direct proof of the incredible strength of hydrogen bonding, holding these molecules together so tightly. But this isn't just about boiling points. This special force, this molecular superglue, is literally what holds our genetic blueprint together. You know the two strands of the DNA double helix? They're connected by millions of hydrogen bonds. They act like the rungs of a ladder, specifically pairing up the bases. And it's the combined strength of all these bonds that makes our DNA so stable. But here's the beautiful part. Because they are individually weak, the two strands can unzip when the cell needs to copy its genetic information. It's this perfect balance, strong enough to hold together, but weak enough to come apart when needed. So let's recap. We have this clear hierarchy of forces, right? Dispersion is the baseline for everyone. Then dipole-dipole adds extra strength for polar molecules. And hydrogen bonding is the super strength version for a select few. The coolest part is that we can use this hierarchy to actually predict the properties of real substances. So let's put what you've learned to the test. Here are 3 different molecules that all have very similar masses. Based on everything we've just talked about, which one do you think has the strongest stickiness, and because of that, the highest boiling point? Okay, let's break it down. Propane is nonpolar, so it only has dispersion forces. That gives it the lowest boiling point, way down at -42 Celsius. Next up, dimethyl ether is polar, so it has dispersion forces plus those dipole-dipole attractions. That bumps its boiling point up to -24. But then you have ethanol. It's got that special OH group, which means it has dispersion forces, dipole-dipole forces, and powerful hydrogen bonding. That's why its boiling point is all the way up at 78 degrees Celsius. See, the hierarchy works perfectly. So from a gecko clinging to a wall, to the water in your glass, to the very DNA inside your cells, these invisible forces are shaping everything. So the next time you see water droplets beating up, or notice that oil and vinegar just refuse to mix, you can see it in a whole new light. Now that you know the rules of molecular stickiness, what else around you suddenly makes a lot more sense?